This lesson is on polymers. We've come across this before when we looked at covalent bonding, and what we need to be able to understand is how our alkenes can join together to make polymers that essentially look like alkanes. We need to be able to recognise the structure and bonding and the way that we represent both our polymers and our monomers as displayed formulae. So here I have my monomers of ethene. So the important point being that monomers, they're just small molecules that have the potential to join together to make a polymer. So these are our monomers, and in this case we're looking at ethene, which we should recognise from our lessons on the alkenes. Now, looking at just one of these molecules, if I draw out the structure, we've got our 2 carbons, we've got our double bonds, and we've got 4 hydrogens around. So each one of these monomers is one molecule of ethene. These are small molecules, they're very easily separated, the forces in between the molecules, so the intermolecular forces, are quite weak. So this means that ethene is going to be a gas at room temperature. So what we've got here is 2 polymers of ethene, and we can see clearly we've got that double bond in the middle joining the 2 carbons. This means that these molecules, they can't actually rotate around that axis, they are fixed as they are. But it does mean that I can break one of those bonds to react the molecules together without actually separating the carbons completely. So what I mean by that is that under certain conditions I can break one of these bonds. You can see that bond's open, but these 2 are still attached by the bond that's left behind. And I can break another bond here, and we can see it takes a lot of energy to break that bond. And then I've got these 2 dangly bonds left over, and what happens is that these ethene monomers join together. I'm just going to show them joining together there, and you can see that they join together, and what we've ended up with here is a polymer. Now this polymer only contains 2 monomers, and it looks very much like an alkane. In fact, essentially it is an alkane. But the interesting point is that we've got this dangly bond out at the end, and technically we've got another bonding site here. So these 2 areas can join together and join onto many, many more monomers as they break that double bond and just one of those bonds, and they join together to make a polymer. So many monomers make a polymer. So this, because it's made of lots of ethenes, it is polythene or polyethene. After our ethene monomers have joined together, they make a polymer. So this is just a joining together of our monomers. So I've got my polymer here, and this is polythene. We can write it as polyethene, although usually we don't include the brackets. When we're drawing the formula for polythene, because this can be any length, we actually need to show that it's any length and it's just made of the monomers that went in. So when we're drawing this polymer, we're drawing it, we've got the 2 carbons, remember there's 1 bond in between because it's now an alkane, and we draw our hydrogens that are attached, and we draw the bonds coming out either end. Those bonds are there even if they're not actually joined as yet. And then we pop this into brackets, and we're going to say that this is a repeating unit, N. N just means however many times. So if we had N monomers, then I would end up with a polymer that had N repeats in it. Polymers tend to be incredibly long molecules, incredibly large molecules, and they therefore have quite large intermolecular forces. You can think of it as larger molecules being a bit stickier. If you remember when we looked at crude oil, things like bitumen and tar, they're going to be stickier than things like our petrol. So our larger molecules tend to be a little bit stickier, a little bit more viscous, and that just means gloopy, they don't run so well. And this tends to make them either a liquid, or if they get to be in long enough chains, then they'll become a solid. at room temperature. And that's when we're looking at things like our plastic, polythene. We know it as a solid at room temperature, and it's a solid because, well, it's built up of lots of small molecules, making a large molecule, and therefore it's changed the amount of intermolecular forces between the molecules, and therefore the boiling point has increased, the melting point has also increased. To summarise, if we want to put this into a chemical equation, I've got my monomers, and they are going to make my polymer. I can also write this as a word equation, so here I have ethene, and this is going to make polythene or polyethene. I've also got, I can write the formulae out, and we tend to use the displayed formulae when we're looking at our alkanes, alkenes. So I'm going to write my displayed formula for my ethene. And I'm just going to put an N there, which is however many. In this case it's 2, but the N is just however many I had, and those are going to make polythene. So I'm going to draw, noticing that there's a double bond because it still needs to be attached together, the carbons still need to be joined, so there's that double bond there, and I'm putting that in my brackets and putting the N there, so however many went in, that's however many repeats come out.